All right, so power diagrams are very similar to system diagrams. It's just instead of documenting audio signal flow, you're documenting power. And the things that you want to, the things that you're interested in power-wise, are you want to make sure that you're not going to trip any breakers, for one. Generally speaking, our stuff does not draw a whole lot of current. Most of our stuff is pretty, low voltage stuff. It's the power amplifiers that tend to do the most damage. But ultimately, what causes a breaker to trip is when the amount of current flowing through that circuit exceeds some threshold. Okay, so current is that energy in motion, right, as it's moving down the wire. And you want to make sure that you are designing a powering system so that everything is able to be powered at its fullest capacity without tripping any of your breakers in your system. There's also another issue of wanting to make sure that you're keeping your power signal as clean as possible, in the sense that you want to make sure that you don't have other stuff that you're sharing power with. So this helps make sure that everything that you're using, that you're powering, is ultimately coming back to a single source in some way, and also documenting any other things that maybe you're not involved in but that might be on your power, so that you can know to either move that to something else or watch out for that when you get into space. Because sometimes when you share power with other things, it can cause problems with your sound system, and you can get noises and hums and things like that. So that's kind of what you're interested in here. Instead of flowing from left to right, in this case we go from top to bottom. However, we kind of draw it from the bottom up. So the things on the bottom are the actual pieces of equipment you're going to use. For example, here's the Mac Mini that they're using for playback, the Audiofire sound interface, the actual LCD monitor. Here's the mixing console. There's a little crossover they're using here, a CD player. And what they're showing you here is this little number next to it is the amount of current that this thing will draw when it's running. And usually you spec this at the worst case scenario. So that's the maximum amount of current that this thing's going to draw. And most electronic equipment will draw the most current when you first switch it on. And then it'll usually kind of settle down a little bit. So ultimately they're saying that in total we're pulling 4.4 amps on this SurgeX unit. And so that's getting fed into this other ETA PD8L along with this other stuff. And in total that's 9.47 amps. And that's being connected to a 20 amp circuit. Okay, so assuming that this is the only thing you're putting on that circuit, and the only thing anyone else is putting on that circuit, then you should easily be able to power all those things without tripping that breaker. Does that make sense? Same thing over here. This is like the amplifiers. So we have this sequencer. It's a three-phase sequencer. There are a total of 6 different breakers on the sequencer itself. There's A, B, C, D, E, and F. Each one of those is a 20 amp breaker. However, they share one leg of, So two of each, they're paired up in a way that shares one leg of that three-phase power. So, so channels A and D are together, B and E are together, and C and F are together. The idea is that you switch all this stuff on in a sequence. You push the button, and A turns on, and then it waits a few seconds, and then B turns on, and it waits a few seconds, and then C turns on. The idea there being that, remember, everything pulls the most current when you first switch it on, and then it kind of settles down. So this way you can only turn on a couple of things at a time, let them get settled, and then you turn on the next thing. So it is possible, and I've seen power diagrams where you're actually pulling more off of the circuit, then you theoretically should be able to, but the reason you're able to do it without tripping the breaker is because of the sequencer. Because not everything is switched on simultaneously. It gets switched on in a sequence. So that's kind of what's going on here, is we're just showing, again, how much current is being pulled on everything. Here's the amps. At worst case scenario, they're going to pull 8.4 amps of current, which is a fair amount. It's not going to do that all the time, but it might do it right initially as you turn it on. So on each of these things, we're 8.1 amps, 16.8, 18.83, and supposedly that this is a 60 amp breaker that is feeding that pair. So we should be fine in all these cases. Okay, so this all goes back to a certain panel that's labeled IGA. So this is a breaker panel somewhere in that amp room probably. And then that panel is fed by kind of a main breaker for the patron's booth. And that panel is fed by another breaker panel that's underneath the thrust sector outside this door, in a little special room there. And that panel is fed by what's called the main RDP panel, which is the big mechanical room again over here. And we're just kind of saying, ultimately, this is the total we're pulling on this. Now, this particular drawing is not fully complete because there's certainly other things that are pulling off of this. But what you want to do is you want to make sure that you're finding all of the different points where a breaker could be that you would be able to access in the building if the worst happens. Because the power company will help you sort out the power up until it gets into your building. And then from there, it's up to you. So once it leaves the building, then it's their problem. But if it's inside the building, it's your problem. So you need to know where are all the possible failure points. You need to know where those exist. So notice how she's saying here where you might find these. So this one's found in the patron's booth. This one's found under the thrust, which is actually out here. But this one's in the cob closet, which is where you'd find it. Okay. And if you notice, like if you look at this particular disconnect over here, or look at this. So it says that this is a 100 amp service here, and it is fed from this thing called RDP 13, 15, and 17. Okay, so each of these is each phase of this is coming from one separate breaker on that from that RDP. So you have to find out where that is. Hopefully you can find building drawings sometimes. It'll tell you. But we could, if we wanted to, we could type into this. If we had to. There's not. We need to add some connectors on this thing to get our tails into it. But anyway. So that RDP, remember that showed up on her drawing, right? Let's see if we can get into there while we're sitting here. David's class, his electronics class, you guys will trace all that stuff. So that's the basic idea. You just want to figure out how much current each of your devices wants to pull and add that all up at each point where there could potentially be a breaker that trips. The breakers are meant to protect you, so if you start pulling too much current down a wire, it eventually might catch on fire. So you'd like to interrupt that before that happens. So you certainly don't want to try to defeat that. It's meant to protect you. So you just need to work around it. If you're finding that you're pulling too much current off something, you need to find another circuit somewhere along the way. This is nowhere near as complicated for us as it is for people who, lighting and MoCo and things that draw tons more power than we do. But it still is something you have to figure out. If you figure this out ahead of time, and you know where everything is going to get connected, it can save you a lot of time and load in. And when you have problems power-wise, you'll have at least some place to start from in troubleshooting it. There's no standard for this. This is just something we've made up. But we have some kind of loose ideas of how we lay things out, and you'll just kind of get the pattern here. I'm not going to make you do one of these for the class, but I just wanted you to kind of see one and be familiar with what it's trying to accomplish. So do you guys have any questions about this? Don't be scared.
How do you tell, are the wall plates labeled?
Like, how do you know what breaker they come from? Sometimes they'll be labeled, and if they aren't labeled, then you could put a label on it once you figure it out. We do have a little circuit sniffer in the lab where you can plug. It's like a little transmitter that you plug into the receptacle at the wall, and then you go and try to find the panel you think it is, and there's a little receiver that you can kind of sweep up and down the panel, and it'll beep when you get to the breaker that it's connected to. So that comes in handy sometimes when you're trying to chase things down, figure out where this is coming from. So we use that pretty often. And as I say, over the years, students have labeled things as they've sorted it out. They put a little label on it. So this comes from here, and then you'll know. Other questions? No? All right.